Over the last decades, many runtime systems have been developed to automate and manage the deployment of applications on what we now call often Cyberinfrastructure resources, which is a pompous way of just saying a bunch of clusters. And an area in which really the development has been extreme is workflow management systems. Here is a screenshot from a website that some of you may have seen, maintained by Michael Crusoe as part of the CWL project, which lists, to the best of his and his collaborators' knowledge, existing workflow management systems, meaning runtime systems that automate the deployment of workflow applications. And that website lists over 300. Now, many of those are now defunct, but many are still actively used. Now, the proliferation of workflow systems is quite stunning and problematic, but that's a topic for another talk. But one thing all those systems need to do, in principle, is to make some scheduling decisions, right? And so the immediate reaction is not to worry. There is an enormous literature on workflow scheduling, many survey articles, in fact. So therefore, things should be good. Scheduling as implemented in those systems shouldn't be difficult. But maybe not too surprisingly, if we look at those systems, we see that the literature has very little impact on practice. And so it's hard to generalize. And again, this is anecdotic, but we looked at a few state-of-the-art popular such systems, and we find that basically they do very vanilla scheduling. They perform list scheduling with random or arbitrary tasks and worker compute node selection, right? And so when we talk to systems people, and again, maybe some of you have had different conversations if you've had any of those conversations, but what we hear in our groups is that scheduling algorithms seem complicated. They often make assumptions that don't hold. There are so many of them, we don't know which one to use. And I should say here, I'm not talking about batch job scheduling algorithms, right? I'm talking about application level scheduling algorithms. We don't have full correct information to provide them good input. And scheduling seems to be that thing on the to-do list of those people who develop those systems, right? So there seems to be quite a chasm between theory and practice. Now, to give some context, let's look at pretty vanilla scheduling problem. So let's consider a heterogeneous multi-cluster platform where every cluster is heterogeneous with some number of compute nodes and connected to the internet via some bandwidth. And here, when I say cluster, of course, I mean maybe a cluster, but more likely a pilot job obtained on a cluster, right, as we heard about in the previous talk. And each cluster can store cache application data, and that's our platform. Now we have a workflow application, which is a directed acyclic graph of tasks. The tasks can be multi-threaded, and they have data dependencies based on input and output files. And initially, let's say that all the data reside at some remote location. And the objective is to minimize makespan, right? So if you're an application scheduling researcher, this is the kind of problems that you write papers about. Now, it's very easy to come up with a bunch of list scheduling heuristics to try to compute a solution to that scheduling problem, right? And there are three axes of decision: task selection, cluster selection, and core selection. So which task do we schedule next? On which cluster do we put it? And how many cores do we give it? Okay. And so here is, for instance, 36 algorithms, which is the Cartesian product of 4 choices for task selection, 3 for cluster selection, and 3 for core selections. Now, none of these are original. The point of our paper is not to come up with yet another scheduling heuristic. And these have all been used in some fashion in the literature. Okay. So here we go. We define the scheduling problem, and very quickly we come up with 36 scheduling algorithms. We could easily come up with 72 of them, or really 400, based on heuristics and ideas that have been used time and again in the literature. Okay. And so what scheduling researchers do then is they come up with experimental scenarios and typically simulate all the algorithms on all scenarios using more or less realistic simulation techniques, which is actually a problem as well for people in practice who look at scheduling results published in the literature and often don't trust those simulation results. And then the scheduling researcher compares the algorithms using some metric. And let's use a very common one. Here we're optimizing makespan, and so we're going to compute the degradation from best. DFB, meaning for each scenario, we compute how far in percentage an algorithm is from the best algorithm for that scenario. So 0 means you're the best algorithm, 100 means you're twice as bad, right? And so an optimal algorithm would have a 0 DFB on all experimental scenarios. And so let's do that again. Here again, I'm putting my scheduling and researcher hat on, and I'm trying to come up with what I could write in a paper about scheduling. So here are scenarios. The table at the top shows 9 arbitrary platform scenarios. Looking at the first row here, configuration P1 has 1 cluster in it, and that cluster has 96 nodes. The speed is 100, the bandwidth is 100. Now, the paper gives details about the units. The speed is the compute speed of a node, and the bandwidth is the bandwidth through which the cluster is connected to the internet. Okay. And then config P2 has 2 clusters, each of them with 48 nodes, right? And so on. We pick arbitrary, in this case, platform scenarios. Most of the scenarios have 3 clusters with different compute speeds and bandwidth. Okay. And then we have to pick scenarios for the workflow. So here, those in our case study, we don't pick them arbitrarily. We actually use real-world workflow configurations. So those are applications from various scientific domains with different number of tasks, different amounts of work. This is the total work in hours of the workflow on a reference machine, data footprints, and then different shapes of the acyclic graph, meaning the task graph, different depths and different maximum width of the levels in the graph. Right. So at this point, we make an argument that we have a reasonably diverse set of platforms and a reasonably diverse and representative set of applications. And that gives us 72 experimental scenarios. Right. And so then we publish results like this one, where on the x-axis, we show all the scenarios. There are 72 of them. And on the y-axis, for each of the 36 scheduling algorithms, we plot its degradation from best in percentage. Again, remember, 0 is the best you can be, right? And the blue line is showing the worst algorithm, and we sort the scenarios by increasing values. So that way we have a smooth increasing curve here, and it makes the graph readable. And so, for instance, on this scenario, workflow instance number 5, platform instance number 1, this is how the algorithms behave. Some are really good. Of course, 1 is always going to be at 0. And then 1 is at about, what is that, 6, right? So this one is 6% worse, right? Perfect. Now, this is a log scale. So here we're talking about tens and hundreds of percent worse, right? And so that spread here is the difference in efficacy of the different 36 algorithms on the same scenario. And so, of course, because scheduling is NP-hard and these are all heuristics, we expect that it's going to be messy like this. And if we were to pick the best algorithm, and here I put best in quotes, we would pick the one that had the best average degradation from best, meaning over all those data points, all those 72 scenarios, which one is best on average. And in this case, it happens to be an algorithm that one of the 36 that I'm plotting in red here. So the red data points are for one algorithm. And we see that indeed this algorithm is at 0 often, but it can be pretty poor. For instance, on this scenario, whichever that is, W1P3, so the first workflow, the third platform, this good on average algorithm fares very poorly. It's more than twice as bad as the best algorithm on that platform. Okay, yet it is the best on average. All right, so the literature is full of scheduling results that are published and that are, I mean, some version of what I just showed here. And so the question is, does this help practice in any way at all? And what we think we hear from the systems people is that this kind of result really does not help convince them to implement scheduling algorithms. Right? There are 2 big problems. Which algorithm to pick. I mean, the red one is the best on average, but in some cases it can be really poor. Right? So that's one thing, which one to pick. And that's only out of 36. What if I had done this over 400 algorithms, right? Clearly, there's going to be a case where the best on average algorithm is absolutely terrible. And that's just because scheduling is hard. And then can we trust these results anyway? The simulations may be naive and may make all kinds of unrealistic assumptions that may not apply in practice. And so we can say for sure, of course, and again, this is only anecdotic, and there may be runtime systems out there that do an amazing job at scheduling. But in our mind, that at least partly explains why so many runtime systems don't pay that much attention to scheduling, even though we would think they would, because that's what they have to do. Right? But turns out they resort to very naive approaches in practice. And so an idea to try to bridge a little bit that gap between scheduling theory and practice is simulation-driven portfolio scheduling. Now, that's a pretty simple and natural idea. The idea is, well, as opposed to being faced with the conundrum or the dilemma of picking one of many algorithms to implement in my runtime system, how about I implement multiple of them, maybe 10, maybe 12, maybe 2. Right? And throughout the execution of my application as automated by my runtime system, maybe many times throughout that execution, I run simulations of my system. So that's right, the system simulates itself to evaluate how the different candidate algorithms in my portfolio are gonna behave. Right? So another way of saying this is that the runtime system simulates all its possible futures using all its possible algorithms, looks at what the simulation says and picks the best algorithm. In our case here, we're talking about the one that minimizes application lifespan, but there could be other metrics of goodness. This algorithm is picked for some short term, and then later on we reevaluate, resimulate. At this point, part of the application has completed, and so we simulate only the application execution that remains and see what happens again, and maybe switch to a new algorithm. So this idea is not novel. It's been proposed in the context of batch job scheduling. And so here are some references that have done this. And the main idea in those works are that they try out different job ordering policies in the batch queue. Okay, and again, excuse me, in this talk, we're not talking about batch job scheduling. We are talking about application level scheduling when we schedule application tasks on resources that may have been acquired through batch schedulers via pilot jobs, for instance. And so the idea is to try different job ordering policies, compute a schedule using each policy. And that's what's called the in quote simulation. It's not quite a simulation, it's just a deterministic computation of a Gantt chart based on the content of the batch queue using some job ordering policy. And then we compute a metric like the bounded slowdown, and then we can pick the best in the near future. So overall, it's the same idea, the idea of using simulation at runtime to see what the future may hold and make enlightened decisions. But here, it's a very different kind of simulation. It's merely computing a deterministic Gantt chart. There is a source of inaccuracy, which is that, as we know, estimated job runtimes in the batch world are notoriously inaccurate. But that's not really simulation inaccuracy, because the real world system also faces that inaccuracy. So it's not really about the simulation being inaccurate, it's about the world itself being inaccurate. And so the question we wondered about is, can this approach, portfolio scheduling, work in our context when the simulation can suffer from all kinds of errors because it simulates network resources, IO resources, cores, and so on, right? And so we can never simulate a system like that perfectly, as opposed to a Gantt chart that we can compute maybe perfectly. And so to answer this question, we implemented a simulator of a workflow management system that can use any of the 36 algorithms I talked about earlier, and to schedule them on a multi-cluster platform. So basically for the scheduling problem I outlined a few slides ago. And that simulator, throughout execution, can simulate its 36 possible futures using, turns out, the fork system call to pick the algorithm that leads to the lowest simulated next span. It does that every time 10% of the total work has been accomplished. So this is a bit strange here because our simulator is our ground truth real system, and then it forks itself to run simulations of its futures, and those are the simulations in which we can inject errors, right? We're doing it this way, that way we can control everything because our real system is a simulation that then simulates itself. So it's a little bit confusing, but that's the only way to really control the parameters. And the second phase of this work, which is future work that we're working on right now, is of course to do this for real, where the real system is now a real system with all kinds of strange and noisy behaviors. Okay. Our simulator is implemented using the range and SimGrid simulation frameworks you may have heard of. If not, I encourage you to look at them. So the first kind of experiments we can do here, and those are not going to be very surprising, is we can say, what if the simulations are 100% accurate? Now we can do that again because our ground truth is simulated, therefore perfectly controllable. And so that allows us to do this kind of experiments. And so in that case, if you know your future perfectly, well, then we expect portfolio scheduling to always be at least as good as what any one algorithm could do, right? And switching which scheduling algorithm you use at runtime should bring some advantage, because maybe different phases of the execution of a workflow could benefit from different scheduling strategies, okay? And so we compared the portfolio scheduling approach that, again, every 10% of the workload, whenever 10% of the workload has been computed, it simulates 36 scheduling algorithms for whatever remains of the application execution, picks the best one, and uses that for the near future. We compare that approach to an oracle that picks the best one algorithm for each scenario. So an oracle that says, I do not change scheduling algorithm at runtime, I pick one, but magically I know which one is the best out of the 36 algorithms. And so we found that out of the 72 scenarios, the portfolio scheduling outperformed the oracle for 56 of the scenarios. So for most of our workflows and our platform scenarios, turns out switching which scheduling algorithm you use at runtime at some point during the execution is beneficial. Right? For 16 of them, turns out using a single algorithm is best throughout the whole execution. Okay. So that's not too surprising. And of course, this is unrealistic because simulations are not 100% accurate. Now, in those results, we every simulation simulates the application's execution until completion. And one concern with this approach is the simulation overhead, which is something that all the previous work has talked about and which I'm going to talk about later on in this talk. But one idea would be to say, why do we simulate the future all the way to the completion? That leads to longer simulation. How about we simulate only the near future? So maybe we make the simulation a little bit myopic, and maybe that's good enough. Right? And so we look at that, and we use the red algorithm, the best one algorithm on average as a competitor. Right? That's the best rational choice a system developer could do to pick a single algorithm to implement in their system in our case study. And now we can measure the improvement in makespan of the portfolio scheduling approach when simulating X% of the total remaining work. For X is 100, which is what the previous results were about, or 90 or 80. Right? So the higher the number, the more we simulate, the more time we spend simulating, which is more overhead, but then we know exactly what the application makespan is going to be because we simulate its execution up until its completion. And so this is one set of results where on the x-axis, we have the fraction of work being simulated. And on the y-axis, we have the improvement over the one algorithm approach, right? So values above 0 means portfolio scheduling outperforms the one algorithm approach when, again, we pick the best on average one algorithm as our competitor. And the different colors are for the different workflows. And for every workflow, we show a violin plot that shows kind of the shape of the distribution with the average, the mean, and the max. And so when we simulate the whole application execution, meaning when 100% of the remaining work, we see what I talked about 2 slides ago, which is, yes, portfolio scheduling always does better because it has the flexibility of changing the scheduling algorithm in use at some point during the execution, and meaning different workflow phases can benefit from different algorithms. That's not always true. For instance, for workflow 5, we see that we don't do much better. But for some workflows like workflow 1, the red one, we see that we can get much better makespan. But the question is, can we get away with not simulating the application execution all the way to its completion? And the answer is that for some workflows we do. So for the red workflow, when we simulate only 90% of the remaining work, we still have very good result. And in fact, we see that the red distribution is almost entirely above zero, even if we simulate only 10% of the remaining work. So for the red workflow, for instance, we can make the simulation very myopic and it still works well. And it's because for that workflow, due to its structure, the scheduling decisions we make early on don't really impact the execution in the later stages. But for some other workflows, like workflow 4, the gray one, we see that's not the case. Looks pretty good so far, but then if we don't simulate at least 80% of the remaining work, then all of a sudden, portfolio scheduling dramatically is outperformed by a one algorithm approach. And this is because here we made the simulation myopic. And for this workflow, because of its structure, what we do, the scheduling decisions we make early on should take into account the execution of the later stages of the workflow. Right? So we cannot really say that it's okay to not simulate the application until its completion because it's okay for some workflows, but terrible for others. Right? So as a result, all the results hereafter, whenever we say we simulate the execution to pick which algorithm to use from now on, we always simulate the execution until its completion, which is bad news for simulation overhead, but I'll come back to the overhead in a minute. So the key question, of course, is that of simulation error. All those results so far were with perfectly accurate simulation, which is never the case. Right? Now, a lot of work has been done in developing accurate simulation frameworks, and the SimGrid project has spent many people and hours on getting that done. But no matter what you do, simulation can never be perfectly accurate. Some very popular simulation frameworks, in fact, are known to be widely inaccurate, which is a topic all of its own, not for today. But in general, the topic of simulation accuracy is very complicated, and there are many aspects. The accuracy of the simulation models, how those models are calibrated, what information is known about the system, and so on. So as opposed to launching into that, what we did in this paper is just say, well, let's just inject uniformly distributed simulation error of increasing magnitude. So whenever the simulation says, I have simulated that using this algorithm, the application will run in 2 hours, we take that number, 2 hours, and we add a uniformly distributed random noise to it, right? And we repeat for many different seeds of the random number generator. And so now we add noisy simulations, and we can rerun the experiments and show similar results. So here, the same kind of plot. Values above 0 mean that portfolio scheduling works. Values below 0 means that it is outperformed by the one algorithm approach, reminding you that our competitor is the best on average one algorithm approach, which it's really unclear how a runtime system developer would actually pick that one algorithm without doing a whole scheduling study. And on the x-axis, we have the simulation noise, right? So 0 is perfect. So this is the same results we showed earlier. But 0.1 is 10% error, 20% error, 40% error, 80% error. Now, what we see is that things stay relatively okay up until 20% error. Now, there are some values below 0, but again, we are comparing ourselves to the best possible choice a developer could use by picking one algorithm out of the 36, right? When the error gets out around 40%, we see that many points are below 0, and at 80% expectedly at this point, the simulation is very inaccurate. Right? And so the conclusion from those results is that even with 20% error, simulation-driven portfolio scheduling seems to be competitive with the best one algorithm approach. Right? And it's really not that bad for 40%. Maybe for the green workflow here, it doesn't look very good. Right? And the good news is that many simulators developed with Ranch and SimGrid have been found, which are, of course, two simulation frameworks I'm personally involved with, have been shown to achieve much lower error in practice. Okay, so the main conclusion is that it seems like portfolio scheduling for this kind of systems may be a feasible idea. Okay, and they have a the potential of resolving or bridging the gap between the scheduling literature and the practice, because at least we remove the need to pick one particular scheduling algorithm to implement. Just implement one, implement a second one, and the system will maybe not use one if it's just never good, and will automatically pick the best one based on the simulations. Okay. Now, one question that people ask at this point, and that's been mentioned in all previous works on portfolio scheduling in the context of batch job scheduling, is that of the simulation overhead. Now, a lot of simulation frameworks exist. Some are notoriously slow, but some have placed a lot of effort in trying to improve speed and scalability, SimGrid being one of them. But that doesn't mean simulation takes zero time, right? So the question is simulation overhead prohibitive in practice? And the answer is basically no, it's not. Here are 5 reasons why. So reason 1 is that simulations are discrete event and not discrete time. And so simulation times can be orders of magnitude smaller than actual execution times. So the simulation of an application may take a minute, but if the application runs for 2 days, well, that's perfectly acceptable. Reason number 2 is that the simulations run concurrently with the application on the machine, for instance, that executes the workflow management system code. And so the only effect of simulation overhead is to delay adaptation. Meaning delay the moment where we say, oh, we should switch to a different scheduling algorithm. And in our results, we didn't pick specific times at which to do the adaptation. Those were very arbitrary, right? So one of the reviewers of the paper said, well, what about doing adaptation at crucial times, maybe whenever a workflow level completes or a new workflow level starts. And so since the paper, since we got that comment, we actually tried this. I don't know if the reviewer is in the room here, but and turns out that makes almost no difference, right? So it seems that the time at which we do adaptation doesn't really matter. And so if we delay it by a minute or 2 because the simulation takes a minute or 2, well, it doesn't really matter. Reason number 3, that the simulations are still pretty fast and they are very low memory footprint, at least using the SimGrid and range systems we've been developing. And so that means you can run them concurrently on a multi-core machine with very high parallel efficiency, right? So simulating 36 algorithms, for instance, like we did in this case study, doesn't take much time at all. Reason 4 is that even if it takes time, because maybe your portfolio of algorithms is 400 algorithms, not 36. Turns out we ran experiments by reducing the frequency of adaptation, meaning the number of simulations we execute. So we did it twice less frequently, and we find that in fact that leads only to small degradations in performance. So it seemed that one way to mitigate simulation overhead in case the first 3 reasons somehow are not sufficient is to simply reduce the frequency at which the simulations are executed. And finally, if all that fails, well, the reason number 5 is that then we can use technique to prune the algorithm portfolio. Those have been proposed in previous work on batch scheduling. And the idea is if the simulations keep saying that an algorithm is poor, maybe at some point we say, well, forget this algorithm for the near future. And then we reduce the size of the portfolio and therefore reduce the number of simulations we have to execute. So the results are encouraging, and there are several interesting theoretical in quote questions. I'm saying quote here because it's all very heuristic. So one thing I just mentioned on the previous slide, which was suggested by a reviewer, which is non-arbitrary ways to decide when to adapt. In all our results, we said whenever 10% of the work has been completed, run simulations of your future, see which algorithm is best, and from now on, use that one. And so the reviewers, as I said, how about adapting whenever a workflow level completes or starts? And turns out our results show that that makes almost no difference, even though it was a good idea. So thanks to the reviewer, they're here. And we thought it was going to make a big difference, but in the end, it's a wash. One thing we want to do is to distinguish different kinds of simulation noise. And the results in the paper are very brute force. We said whenever the simulation says the application will take 2 hours, we add to that noise. And we do that differently for every simulation. Now that's actually pessimistic because if we simulate 36 scheduling algorithms, we're going to apply the same kind of, suffer from the same kind of error for all those simulations, meaning if we underestimate the compute speed of a remote cluster, we are going to underestimate it in the same way for all algorithms. So in fact, one thing we're doing right now is refining the way in which we inject noise, which improves the results based on the result compared to the results published in the paper. And one interesting thing is, after all, why not use portfolio scheduling to solve dual objective or multi-objective scheduling problems, for instance, optimizing make span and energy, right? So we simulate all the possible futures for all possible algorithms. Each simulation returns the make span and the energy consumption. And based on that, we make decisions to achieve some, I don't know, Pareto optimization of the two objectives, or minimizing one by keeping another one constrained, and so on. So I think this idea of having a portfolio of algorithms and use simulation to try to achieve all kinds of different goals is probably pretty promising. Now, this paper is really a preliminary investigation to see whether there is any possibility of this approach being feasible in practice for those kind of systems. The answer seems to be yes. And so our current work is to make this work in practice. And so we are currently working on producing a prototype of the parcel workflow management system developed at the Argonne National Lab and University of Chicago that does portfolio scheduling as I just described. And a very interesting idea in practice, which to me is the most interesting question in all this, is that of simulation error forensics. So the real world system runs and at some point says, let me simulate my futures. We say, oh, based on all those simulations, I pick algorithm 8 now, and now I use it for real, right? So now we do it for real for, let's say, an hour. And after an hour, now we can compare what happened for real with what the simulation had said would happen in the future, right? And so that allows us to confront the simulated execution to what really happened. And based on that, quantify sources of error and introduce bias in future simulations to try to automatically mitigate the simulation error as the application progresses, right? So there's a lot of interesting questions there. It's clearly challenging, but to me, that's probably going to be the most interesting contribution that's going to come out of implementing all this in practice as part of a real system. Again, the real system here being parcel. Okay, that's all I had to say. In case you're interested in those various projects, the Ranch and the SimGrid projects are about simulation, and here they are. And also the workflow instances used in this work were produced from the WF Commons workflow. I forget what the tagline is for that website. It's basically a website with workflow instances, automatic generators of synthetic instances, and all kinds of good stuff. Okay. Hopefully I'm somewhat on time.
Okay, so this was the last talk. Are there any questions? What I find interesting was that when you mentioned the fact that early decisions may actually influence the quality of the final decision, it somehow reminds me the same problem that you have when you are doing some kind of meta-heuristic optimization, and you may end up in some local optima, and in that case you need to do some random walk or something like that to escape the minima. So maybe
in this case, we looked at those workflows for which the results look bad when you do that, like the gray one. And typically in this case, in these results, it's about data. So it turns out you move a massive data file to some small cluster and it's fine. But then turns out that massive data is also used later on by a bunch of tasks. And then you have to move that, to copy that file again to another cluster to achieve more parallelism. But then you waste a bunch of time doing that, for instance. So it seems very difficult. It seems always very idiosyncratic, and by inspecting the workflow structure, you understand why it happened, and it makes sense. But it would be very difficult to try to characterize workflows in, oh, for that workflow, it's okay to be myopic, but for that workflow, you should simulate the whole thing. That's probably a very difficult question. Yeah. Okay, it's exactly that. If you were to simulate, if the workflow were to abort at halfway, you would have done a perfect job and not seen that effect later on in the execution.
Yeah, I thought this was really interesting. It's kind of in line with experiences I've had, but I wanted to know, do you have a sense of like, what is the threshold at which simulation costs start to become problematic?
Simulation overhead?
Yeah.
You know, it's difficult to answer that question definitively, because of course it depends on the number of algorithms in your portfolio, right? So if you have 8 algorithms in your portfolio and you're running your system on an 8-core machine, then you just parallelize it. It's perfect. I don't, but my guess right now, and of course we're going to see that when we do it in practice, my guess is it doesn't quite matter if your application is somewhat long, because as I said, the simulation overhead, and we're talking minutes here, we're not talking hours, the only effect it has is to delay the time at which you're going to switch scheduling algorithm. But the application is not paused while you're on the simulation, right? So the application is running for you, and you say, okay, let me simulate the future. You start those simulations and they run, but stuff is going on. You don't terminate application tasks as they run. And whenever the simulation comes back, you're like, okay, from now on, I'm setting the algorithm to number 7. And since it seems that the time at which you make those adaptation decisions doesn't really matter, I'm going to go on a limb here and say that as long as your overhead is orders of magnitude lower than your overall execution time, you're going to be fine anyway. And so with the SimGrid and range simulators, for most scientific workflows, for instance, that's true, right? The simulation execution time is orders of magnitude lower than the application execution time. So my take on it is that simulation overhead is not going to be an issue unless you go crazy and you have a portfolio of 400 algorithms, and then okay, maybe that's a little bit of an issue, but in practice I doubt it's ever going to be an issue. Now, and here I'm resting on the decades of work on SimGrid to make SimGrid as crazily fast as possible, right? With a different simulation framework, some are orders of magnitude slower than SimGrid, then it would definitely become an issue. But with that simulation technology we're using, I don't see it as an issue at all.
Excellent, thank you.
Sure.